Hey everyone, and welcome back to the Nerdwork Nexus. Today, Tokamak fusion power.
I think you're going to be surprised at just how close that future might be.
Oh yeah,
We're talking harnessing the same force that drives the stars.
exactly. We've got some seriously exciting news and breakthroughs to unpack, so let's get right to it.
All right.
You know, when I first heard about tokamaks, I pictured a giant futuristic donut.
Okay.
Turns out I wasn't far off.
That's a great way to visualize it.
Like, really?
Yeah, a tokamak is shaped like a donut or a torus, to be precise. It's a vacuum chamber, but not just any vacuum chamber.
Right.
This one's designed to contain superheated plasma. You need plasma to get those fusion reactions going.
So we're all engineers and STEM enthusiasts here, so I think we're familiar with plasma.
Right.
But for anyone tuning in who needs a refresher...
Oh, it's the fourth state of matter, beyond solid, liquid, and gas.
Okay.
Imagine electrons stripped from their atoms,
Whoa.
creating this swirling sea of charged particles.
Wow.
And here's the kicker. To achieve fusion, you need to heat this plasma to over 150 million degrees Celsius. That's 10 times hotter than the sun's core.
Okay. Yeah, that puts things in perspective.
Yeah.
So walk us through how we got here. Where did the idea for tokamaks even come from?
It all started back in the late 1950s with a group of brilliant Soviet scientists.
Okay.
They came up with the term tokamak, which is a Russian acronym for toroidal chamber with magnetic coils. Those magnetic coils are the real stars of the show.
So those magnetic coils are what keeps this superheated plasma contained.
Exactly. Picture this.
Yeah.
Powerful magnets encircling that donut-shaped chamber,
Okay.
creating an invisible force field. It's the only thing stopping the plasma from instantly touching the chamber walls, which would cool it down and halt the whole fusion process.
Like an intricate dance between intense heat and powerful magnetic forces.
It is.
So tell me, how did those early tokamaks perform? Was it clear from the get-go that this was a breakthrough?
Those initial experiments showed some real promise.
Right.
I mean, the T1, the very first operational tokamak,
Right.
proved that the concept itself was viable. This led to researchers all over the world embracing the tokamak as the go-to design for fusion research.
Interesting.
Yeah.
And from those early days, what have been some of the most notable advancements in tokamak technology? I know we've got listeners out there who are really deep into this stuff.
Oh, absolutely.
Yeah.
After the T1 came the Tokamak fusion test reactor in the U.S.
Okay.
They managed to reach incredibly high plasma temperatures.
Wow.
And then you have the Joint European Torus, or JT, over in England.
Right.
They actually achieved significant fusion power output. Japan's JT60SA is another major player pushing the boundaries of what's possible.
So it's amazing to think that those early successes sparked a global effort to unlock fusion power.
It is.
But here's what I find fascinating. Even with all the technological leaps,
Yeah.
the basic principle behind a tokamak hasn't really changed, right?
You're absolutely right. The
Yeah.
core concept remains the same. Using those powerful magnetic fields to trap and heat plasma to the point where fusion can occur.
Right.
But what has evolved dramatically is the sheer precision and sophistication of these machines. We're talking about superconducting magnets, specialized materials that can withstand those extreme temperatures.
Wow.
Even the control systems that allow us to manipulate the plasma have become incredibly advanced.
All of which brings us to some exciting news out of France. Talking about the West tokamak. They just smashed the record for plasma duration.
Right. They managed to maintain plasma for a whopping 22 minutes.
22 minutes. Incredible.
It is.
But for our listeners who may not fully grasp the significance,
Yeah.
can you break down why this is such a big deal?
It's not just about breaking records.
Right.
Maintaining stable plasma for extended periods is critical for achieving the ultimate goal, a self-sustaining fusion reaction.
Okay.
You see, plasma is inherently unstable. If you can't maintain control, you won't be able to sustain the reaction long enough to generate any usable energy.
So a longer plasma duration suggests we're getting closer to that holy grail of fusion energy.
Exactly.
Right.
Imagine you're trying to keep a basketball spinning on your finger.
Okay.
It takes constant effort and precision to prevent it from falling off.
Right.
The longer you can keep it spinning, the better your control.
Okay, that's a great analogy.
Yeah.
Now let's dive a bit deeper into the mechanics of a tokamak.
All right.
How does this whole process actually work?
Let's go back to that donut-shaped vacuum chamber.
Okay.
Inside, we start with a gaseous fuel, typically a mixture of deuterium and tritium. These are both isotopes of hydrogen.
Why those specific types of hydrogen?
Because they fuse more readily at the temperatures we can achieve in a tokamak.
Interesting.
We're talking about recreating conditions found at the core of the sun, remember?
Oh, yeah.
And that's where those powerful magnetic coils come in.
Right.
They generate a magnetic field to confine the plasma.
Right. The magnetic field keeps the plasma from directly contacting the chamber walls.
Yeah.
But how does the gas actually become plasma? What's that process like?
Pump a massive electrical current through the chamber,
Okay.
and that ionizes the gas.
Mm-hmm.
This strips electrons from atoms, creating the plasma we need. Then comes the tricky part, heating it to those mind-boggling temperatures.
And that's where things get really interesting.
Absolutely.
Yeah.
We use various heating systems like powerful radio waves and beams of neutral particles.
Mm-hmm.
They raise the plasma temperature to millions of degrees Celsius, and at that point, something incredible happens.
Yeah.
The deuterium and tritium nuclei overcome their natural repulsion and collide with such force that they fuse, forming helium and releasing a tremendous amount of energy.
So we're essentially creating a miniature star in a donut-shaped bottle.
One of the biggest challenges is managing plasma instabilities.
Yeah.
It's inherently turbulent. Think of it like a swirling tornado of superheated particles.
Okay.
One wrong move and you could have a major disruption.
What happens then?
Essentially, you lose plasma confinement.
Okay.
It's kind of like a mini explosion inside the chamber.
So researchers are in a constant battle to maintain stability and prevent those disruptions.
Exactly. They use complex simulations and models to predict these instabilities.
Right.
And are always working to refine the control systems that keep the plasma in check.
It sounds like an incredible feat of engineering and physics.
It is.
And speaking of ambitious projects, let's talk about ITER. I think this is what a lot of our listeners have been waiting for.
ITER is truly a landmark project.
Yeah.
It stands for International Thermonuclear Experimental Reactor, and it's the world's largest tokamak.
Oh, wow.
It's currently under construction in France.
And it's more than just a bigger tokamak, right?
Oh, yeah.
What makes ITER so special?
It's a massive collaborative effort involving 35 nations. Half the world's population represented in this single project.
Wow.
It's twice the size of the largest existing tokamak and has 6 times the plasma volume.
Goodness.
It's a testament to the global commitment to achieving fusion power.
What are the key objectives of this mega project?
One of the main goals is to achieve what's called a burning plasma.
Okay.
This is where the fusion reactions themselves produce enough heat to sustain the process.
Mm-hmm.
Imagine a fire that keeps burning without needing any additional kindling.
Okay, so self-sustaining fusion.
Mm.
That's the dream, right?
Exactly. And ITER aims to not only achieve this burning plasma state,
Right.
but also generate 10 times the energy it consumes.
Yeah.
We're talking about 500 megawatts of fusion power.
Wow. So if ITER succeeds, it'll be a giant leap toward making fusion power a practical reality.
Absolutely. But achieving a burning plasma is just one piece of the puzzle.
Okay.
ITER is also designed to test a process called tritium breeding.
Okay, I'm not familiar with that one.
Well, remember how tritium is one of the fuels we use for fusion?
Mm-hmm.
It's actually pretty rare on Earth.
Is it?
So for fusion to be truly sustainable, we need to find a way to produce tritium during the fusion process itself.
Okay.
ITER will be testing techniques for breeding tritium from lithium right within the reactor.
So it's like creating a self-replenishing fuel source.
Precisely.
And that's not all.
No.
ITER will also be exploring the safety and environmental aspects of fusion energy. We touched on this earlier, but for our listeners who may have missed it, why is fusion considered such a clean energy source?
It doesn't produce any greenhouse gases, so it won't contribute to climate change.
Right.
And unlike nuclear fission, there's no long-lived radioactive waste to deal with.
So no carbon emissions and no nuclear waste headaches.
Right.
It does sound like the ideal energy source.
But as you can imagine, a project of this scale and complexity hasn't been without its challenges.
Right. We've all heard about the delays and budget concerns surrounding ITER.
Right.
What's the latest on that front?
It's true that ITER has faced delays and cost overruns.
Uh-huh.
Coordinating 35 nations and managing a project with millions of components isn't easy.
Oh, I bet.
But the project is moving forward,
Oh.
and the scientific community remains optimistic about its potential.
What's the timeline looking like?
Well, I think it's important to manage expectations. Even with the incredible progress we've seen, commercially viable fusion power plants are still a few decades away.
What are the biggest challenges standing in the way?
achieving sustained fusion reactions
Okay.
that generate a net energy gain.
Mm-hmm.
We're still at a point where we're putting more energy into the process than we're getting out. To make fusion power a viable energy source, we need to reach a point where the energy produced by those fusion reactions surpasses the energy required to initiate and maintain them. ITER is designed to demonstrate this, but it's a highly complex scientific and engineering challenge.
Okay, so energy output is a big one.
Yeah.
What else is on the to-do list for fusion researchers?
Well, another major challenge is developing more efficient and cost-effective technologies for plasma confinement and heating. Those massive magnetic coils and powerful heating systems we talked about, they're currently very expensive to build and operate.
I can imagine.
Yeah.
We're talking about cutting-edge technology here.
Right.
So it's not just about making fusion work, it's about making it work affordably.
Absolutely. For fusion power to compete with other energy sources, it needs to be economically viable.
Okay, so we've got energy output and cost effectiveness. What other challenges keep fusion scientists up at night?
Well, there's the ever-present challenge of materials science.
Okay.
Remember, we're working with incredibly hot energetic plasma.
Right.
You need specialized materials that can withstand those extreme temperatures and radiation for extended periods.
I imagine finding those materials is no easy feat.
You're right.
Yeah.
Scientists are constantly researching new materials that can survive the intense conditions inside a fusion reactor.
Right.
It's a crucial part of making fusion power a long-term solution.
Okay, so we've talked about the challenges, but let's not forget why we're all so excited about fusion in the first place.
Yeah.
Even if it's a few decades out, why should we be optimistic about its potential?
The potential benefits are immense. Starters, we're talking about a near-limitless fuel source.
Okay.
Deuterium, one of the hydrogen isotopes we use for fusion, can be extracted from seawater, which covers over 70% of the Earth's surface.
Wow.
And while tritium is rarer, remember we talked about breeding it from lithium?
Right, that self-replenishing fuel source we discussed earlier.
Exactly.
So, unlike fossil fuels, we're not talking about a finite resource.
Exactly. Fusion has the potential to provide us with a truly sustainable energy source for generations to come.
And what about the environmental impact?
Yeah.
Why fusion is considered such a clean energy source?
Unlike fossil fuels, fusion doesn't produce any greenhouse gases.
Okay.
This means it wouldn't contribute to climate change.
Right.
And unlike nuclear fission, it doesn't produce long-lived radioactive waste, eliminating those long-term storage concerns.
So no carbon emissions and no nuclear waste to worry about.
And we can add safety to that list as well.
Oh, really?
Fusion power plants would be inherently safe. There's no risk of a meltdown like you might see in a fission reactor.
Because the reaction can be stopped quickly if needed.
Precisely.
Yeah.
And without those runaway chain reactions, fusion power offers a level of safety that's hard to beat.
So we're looking at an energy source that's safe, clean, and virtually limitless. It sounds almost too good to be true.
It's understandable to be skeptical.
Yeah.
It's a bold vision for the future. But that's precisely why research and development in this field is so critical.
Right.
Thousands of brilliant minds around the world are dedicating their careers to making this dream a reality.
And with projects like ITER paving the way it does feel like we're heading in the right direction.
It does.
What are your thoughts on the role ITER plays in pushing this technology forward?
ITER is truly a remarkable undertaking. It's a testament to what's possible when nations come together to solve global challenges.
Yeah.
Despite the delays and budget concerns, ITER is providing invaluable data and insights that will shape the future of fusion power.
So while we may not be plugging our toasters into a fusion power outlet next week,
or even next year.
Right. But it sounds like the long-term outlook for fusion power is incredibly promising.
I'm optimistic.
Yeah.
Remember, it wasn't that long ago that things like smartphones and the internet seemed like science fiction.
That's true.
Technology has a way of advancing rapidly. There are two areas which push the boundaries of what we thought was possible with fusion. The first one might surprise you because it takes us beyond the traditional donut-shaped tokamak design.
Hold on. We spent this whole episode talking about tokamaks. Are you telling me there are other ways to achieve fusion?
There are, and one contender has been gaining serious traction. It's called a stellarator.
A stellarator that sounds like something straight out of science fiction.
It does have a certain ring to it, doesn't it? But stellarators are very real, and they offer some compelling advantages over tokamaks.
Can you break down the differences and why haven't we heard more about them until now?
Both tokamaks and stellarators use magnetic fields to contain plasma, but their approach is slightly different. Remember those plasma instabilities and disruptions we talked about in Tokamaks? Those sudden losses of control that can be a real setback for fusion
Ah,
experiments?
those mini explosions inside the chamber.
Right. Well, stellarators have a unique design that addresses this head-on. They use more complex, twisted magnetic field coils, which create a more stable plasma environment.
So accelerators are designed to be inherently more stable, less prone to those disruptive events.
That's the idea, and this stability advantage is a game changer because it could lead to more reliable and efficient fusion reactors.
Okay, so if accelerators are so stable, why haven't they become the dominant force in fusion research? Why are we still focused on tokamaks?
The answer lies in the complexity of those twisted magnetic coils I mentioned. Building a stellarator is significantly more challenging than building a tokamak. It requires an incredible level of precision engineering and advanced manufacturing techniques. But the good news is that recent advancements in computing power and manufacturing have made building stellarators much more feasible. As a result, they're attracting a lot more attention in the research community.
Will we eventually see them eclipse tokamaks as the go-to technology?
It's too early to say for sure, but they definitely offer a promising alternative route to achieving practical fusion energy. And what's even more encouraging is that research in both tokamaks and stellarators is actually feeding into each other, leading to progress on both fronts.
It's like a friendly competition pushing the boundaries of fusion science.
Exactly. Now, are you ready for that second groundbreaking development, the one that really shakes things up in the world of fusion?
You bet, I'm all ears.
This one goes right to the heart of the fusion process itself. Remember deuterium and tritium, those hydrogen isotopes that fuel fusion reactions.
The dynamic duo of fusion fuel.
Right. Well, researchers are exploring a type of fusion that doesn't involve tritium at all.
Wait, no tritium, but we've been told it's essential for fusion.
It is for the type of fusion we've been discussing so far, but there's another possibility, a reaction that fuses deuterium with deuterium creating helium-3 and a neutron.
So it's like a deuterium double feature, but why is this tritium-free fusion such a big deal?
It offers some major advantages. Remember how we talked about the challenges of tritium breeding and the fact that it's radioactive? Those are significant hurdles for making fusion power truly sustainable and safe.
Yeah, those were some of the trade-offs we discussed earlier.
Well, with deuterium fusion, those concerns essentially vanish. Deuterium is readily available in seawater, and this type of fusion produces far less neutron radiation, making it even cleaner and safer.
Wow, so we're talking about an even cleaner and more sustainable form of fusion power.
That's the potential. It's still in the early stages of research, but the implications are enormous.
So as we wrap up this episode, what's the key takeaway for our listeners? What should they be thinking about as they ponder the future of fusion power?
I think the most important takeaway is that fusion power is not a static concept. It's a dynamic, evolving field with multiple pathways to success. Tokamaks are still a major player, but stellarators and tritium-free fusion offer exciting alternatives that could accelerate our progress toward a fusion-powered future.
And while commercially viable fusion power plants may still be a few decades away, the research and development happening right now is setting the stage for a truly transformative shift in how we power our world. It's a future where clean, safe, and abundant energy is a reality, not just a dream.
I couldn't agree more, and who knows, maybe one of our listeners will be the one to make that breakthrough discovery that finally unlocks the full potential of fusion power.
That's a fantastic thought.
Oh.
Well, on that inspiring note, we've reached the end of our Tokamak fusion power journey. Thanks for joining us on this exploration of fusion power. We hope you found it as fascinating and thought-provoking as we did. Until next time, keep those minds curious and never stop exploring the frontiers of science and technology. From all of us here at the Nerdwork Nexus, stay nerdy, and we'll catch you in the next episode.